So this is just a brief introduction on the grid-based search algorithms. Moving ahead, we have incremental search algorithms. So just going back once more, here we have what we see is that the entire environment and how it's laid out is known to the algorithm well in advance. So it knows where the obstacles are and everything in advance, and then it starts searching. But what happens if something comes up here halfway through, or there is a new obstacle that pops up? In those conditions, these grid-based algorithms can struggle. So then you have something called as an incremental search, where, as I mentioned, just explained, the search space is not known a priori. So the search space is updated as and when new information becomes available. So now to design collision-free paths along in such a space, a collision detection algorithm is also incorporated within the search. And then the configuration space is randomly sampled to generate a path to the nearest destination. So that would be something called an example would be RRT. So that is rapidly exploring random trees. And that's also a very commonly known technique. Here I'm showing the most basic example of an RRT algorithm. So the origin is where my mouse pointer is right now, and it has to go to this cross, that is the destination. And as the name says, rapidly exploring, so it starts exploring rapidly. So it starts building a tree at all the leaf points, and the idea is that eventually you are going to reach this destination, and once it has the destination, it knows that, okay, I have a collision-free path, and that can be used for that can be used as a reference path to go from source to destination. So I just let this animation run through once more, and you can see that how the random tree expands. And the good thing about this incremental search is that if we're halfway through the search, if a new obstacle pops in here, basically the search will stop growing along here, and then it will try to come up with a path maybe coming from here or going around the new obstacle. So again, the example here is the most basic RRT implementation, but you can add a lot more heuristics, make it a lot smarter to be suitable for path planning applications or autonomous vehicles. So these were the first two kinds of techniques that you can use for designing or planning paths for a vehicle. The next would be something called as a polynomial fitting. So the space around the vehicle is basically a coordinate space in X and Y. And what we can do is we can describe this coordinate space or the path along which the vehicle has to travel on this coordinate space as clothoids, which are a geometric shape, and polynomials. So the path can be described as a polynomial in X, and the higher the degree of the polynomial, so higher the value of n, the more complex curves you can define. And then if you have the coordinate space of your initial point and the final point, an optimization algorithm can be designed that can compute the different a's, so the coefficients of each power of x for any given transition from xi to xf. And once you do this optimization, you can store these a's in a lookup table and then use them later on just to come up with the polynomial path. So for example, what we have in the plot here is a quintic polynomial fitting. So it is a polynomial of a degree 5. So you have a0, a1x, a2x, a2x x square, etc. up to a5 x raised to the power of 5. And then the arrow here is the initial position of the vehicle, and the arrow here is the final position that it needs to go to. And then an optimization routine can be used to come up with a fifth order polynomial that will kind of come up with a curved path from the position here all the way here, right? And so the good thing in this is you can do this optimization offline. So that is when the algorithm is being built, and you can save all of these coefficients, a to the 1, a2, a3, etc., for different transitions in a lookup table. And then in the real-time application, rather than doing this optimization again and again, the task of the path planner is just to pick out these coefficients. So that's also a quite commonly used technique in the initial first generation of autonomous vehicles. to generate trajectories for an autonomous vehicle. And moving ahead, this is probably another very well-known and well-researched technique. So it's basically constraint optimization. And one of the most famous technique that falls under this category would be something called as a model predictive control, where, as the name suggests, it uses a model of the environment and the vehicle. It has some kind of predictive capabilities, and then using this model predictive control logic, it runs an optimization and tries to come up with a path. And the advantageous thing about this technique is you can kind of have a systematic way of handling the dynamics of the vehicle. You can mathematically describe the environment around you. You can describe collision avoidance constraints. And then the optimization considers all of these things within a mathematical framework to come up with the path. And the output of this constraint optimization is a feasible and collision-free path. So it does the collision check. It sees that the vehicle dynamics are respected, and then it comes up with a path that is feasible and also collision free. So that's quite advantageous for an autonomous vehicle application. So what that would look like is, it's kind of difficult to visualize or explain just via photographs, but I try here. So for example, you have the blue vehicle here, which is the host vehicle, so the autonomous vehicle. And then you have the red, which is a moving obstacle. So you see snapshots of it in time. So it was at position here, 50 at T1, then it kept moving ahead, T2, T3, T4, T5. And then what you see here is the paths that are generated by the model predictive control in real time. And then in blue, you see the actual path that it follows. So in green, you can see the different paths that it generated based on what kind of environmental perception it saw at that given time. And then, so the initial path was straight going ahead, but then you see as the vehicle moved ahead, it had to go around it, and then it successfully navigated it. So at snapshot T5, the obstacle vehicle is somewhere at 160 meters, but our host vehicle has already overtaken and gone ahead. And this optimization would look something like this if you would want to visualize it in real time. And you see that this is the initial position, and this is the final position that it needs to go to. And then the optimization comes up with all these different paths that you see in this animation, and then it selects the final path going from the initial point to the final point. So this is just a very basic introduction to model predictive control based path planning techniques. It's catching a lot of traction nowadays because we have more and more computational capabilities, and we can also successfully incorporate the vehicle dynamics and environment, etc. So it's quite famous nowadays. So just as a summary on the different path planning techniques. So initially I talked about the grid-based search, and what you had there was you could guarantee collision-free paths, and we could kind of import all the techniques available from robotics, so you could already incorporate them and take advantage of the developments that are there. But the grid-based paths are very difficult to incorporate the vehicle dynamics within it. So it's not very suitable for autonomous vehicle applications where you have occupants sitting inside. So you have to respect the acceleration demands, the constraints of the powertrain, etc. And also it's difficult to put constraints on the motion of both the vehicle and the obstacle. So this is just some things to consider while designing paths using grid-based algorithms. Then moving on to incremental search. To summarize, again, we can guarantee collision-free paths, and the new algorithms developed under the RRT techniques can also incorporate the basic kinematic constraints of vehicles. However, some of the shortcomings of these techniques are that the path developed by the RRTs are generally very jerky, so they are not smooth paths. So then if the vehicle tries to actually follow this path, the motion will be very jerky, and then it will not be comfortable for the vehicle. So it cannot really be applied to a real world vehicle. So you need another set of processing to ensure that the path is smoothened. And also these techniques, the computational complexity scales very rapidly with the number of traffic members you have. So for example, if the algorithm takes 1 millisecond to solve when with no traffic around, it will maybe become 10 milliseconds with one traffic member and maybe 200 milliseconds with 5 traffic members. So that's kind of non-desirable in real-time applications where you might want the path to be available at every sampling time of, let's say, 20 milliseconds. And also because of the very nature of this path planning technique, it's unsuitable for evasive maneuvers, because the configuration space only looks at neighboring configurations and it doesn't look at like big jumps in the vehicle's configuration that might be required for performing evasive maneuvers such as emergency braking, evading traffic with a very violent steering action, etc. Then moving on to polynomial fitting, the optimization can be moved offline. So that's quite good because then you can do all your search while the algorithm is developed, and in real time, you don't have any computational requirements. Because it is an optimization based technique, you can ensure that the paths or the coefficients that you are generating are optimal. However, it is very difficult to incorporate obstacles in this technique. It's kind of difficult to ensure or guarantee that the paths generated by polynomial fitting are collision free. And also, it's difficult to find a correlation between the actual vehicle dynamics and the coefficients of the curve. So how the A0, A1, A2, etc., how they relate to the acceleration, braking, yaw dynamics of a vehicle, it's quite a tricky challenge. And finally, moving on to constraint optimization, some of the benefits it provides is it provides a way of systematically handling constraints and dynamics. And because it's an optimization based technique, you can kind of have an upper bound on the computation time. So you can say that just tell me what is the output of the optimization, let's say at every 20 milliseconds, even if the optimal solution is not found. Some of the shortcomings or challenges for this technique is the complexity of the optimization is very sensitive to the number of constraints. So if you have very complex road geometries or very complex collision avoidance constraints, the optimization might be very tricky to solve. And also the complexity of the optimization or the computational requirements are linked to the accuracy of the model. So the higher the accuracy of the vehicle model you have, the better will be the paths that are designed, but it also will require a lot more computation. So what we can summarize is looking at path planning techniques for autonomous vehicles. There are many techniques, no perfect technique available, all have their own benefits and shortcomings. And again, for an autonomous vehicle, while designing or coming up with an algorithm or an architecture, one has to consider these different characteristics and then make a decision on what technique to use. So this was just a brief introduction on path planning. So once the path is planned, what it provides is collision-free points on the road that the vehicle has to follow. And that's where the path tracking comes into picture. So that where the collision-free reference path from the path planning has to be followed accurately via controlled manipulation of the steering, throttle, and the brakes of the vehicle. So you can get this reference path from the path planner as either a trajectory or a path. And the difference between a trajectory and path is quite subtle, so I'll just explain it here. Essentially the reference or what the path planner computes is a set of points on the road. If this set of points are parameterized in terms of time, so it says that you have to be at this coordinate point at time t1, and then the next one at time t2, and next time at time t3, etc. If it's designed or parameterized in terms of time, it's called a trajectory. And if it's parameterized in terms of path length, it is called path, right? So now based on how or what kind of path planner one has designed, you might either get a reference trajectory or you might get a reference path. And then the tracking algorithm has to be capable of accurately following this reference trajectory or the reference path as soon as possible. And Path tracking is a bit more mature field for automotive compared to the previous three parts of the autonomy stack that I just discussed. And there are a lot of control methodologies available. And some of the desirable characteristics one would like from a good tracking algorithm would be, again, a real-time capable. It has to run at a higher sampling rate than the path planner or the perception modules. It has to be robust, so it has to run in different environmental conditions, has to run as well in a new vehicle as it has to run in an old vehicle. It has to run robustly and accurately in a wide range of operating regimes: sunny, wet, damp conditions, snowing, rain, slopes going uphill, downhill, etc. And a desirable quality would be to have a systematic tuning of parameters. And what that allows is that you can kind of tune your algorithm to different settings, and based on what operating regime it is operating in, you can tune your parameters based on that. So these are some of the qualities or characteristics desired from path tracking algorithm or a trajectory tracking algorithm. And I'll just talk about a few things to consider about tracking algorithms. So the first thing is, what kind of vehicle model do you choose for designing a controller? And there's always a trade-off between model order and model accuracy. And so if you use a low order model, you might suffer in accuracy. But if you use a very high order model, you might require a lot of computation, and it might be unsuitable for controller development. So it's always a trade-off. And then moving on to vehicle models, there are quite a few different vehicle models available. The most basic one is just based on the geometric constraints of a vehicle. So if you just imagine the four-wheeled vehicle as a rigid bar that is connected by wheels and a single wheel at the front and the back, and then you can just describe the geometric constraints of the vehicle and use that to design controllers that will be for tracking a path. So you can provide a steering angle to the front wheel, and then you have the wheelbase of the vehicle, and then you assume that the vehicle always turns around the rear axle, and then you use that to come up with a tracking algorithm. Likewise, you could use a slightly more complex, which is called as a kinematic bicycle model of a vehicle, where again the four wheels of the vehicle are compressed into just a single wheel on the front axle and the single wheel on the rear axle. And here you look at the kinematic constraints of the vehicle in terms of what heading angle it can achieve, and then you come up with an algorithm to track the path or trajectory based on this kinematic vehicle dynamics. And then moving on to finally the more complex models, which are based on the dynamics of the vehicle. So they look at the something called as a side slip of individual tires. They look at the tire dynamics. They look at the lateral acceleration, yaw rate, and these dynamic properties of the vehicle to describe the vehicle behavior. And then this dynamic vehicle model is used for coming up with control algorithms. And again, there is no sure short answer of which vehicle model should be used. It all depends on what kind of control problem that needs to be solved, and what purpose we are needing to solve. So for example, if we want to achieve a simple cruise control system, and then the dynamics of the vehicle are not very important, you can just use a geometric model of a vehicle. However, on the other end of the spectrum, if you want to use or even want to develop a tracking algorithm for maybe driving along very twisty roads and maybe in challenging conditions, it's very important to know what are the dynamics of the tire. And there it will be beneficial to use a more high fidelity model or that considers the dynamics of the vehicle. So that's one of the considerations while developing tracking algorithms. I'll just run through a few well-known and commonly used techniques for devising tracking algorithms. So the first family of controllers will be based on the geometric and kinematic models that I just talked about. So, and how they work on is, for example, they use something called as follow the carrot approach. And how that method works is, for example, let's say you have this red curve, which is the reference trajectory or path that the vehicle needs to follow, and the vehicle is somewhere in this configuration or pose. So we look at a carrot point, which is a point described where, so at the look ahead distance in front of the vehicle, the point on the path that we want to actually reach. And then the orientation error is described as the error between this look ahead, between the imaginary line joining the look ahead distance and the orientation of the vehicle. And then you have something called as a lateral error, which is defined as this perpendicular distance. And then the idea is to use simple control techniques to reduce this orientation error or the lateral error. So the controllers that one comes up with, or the control law that one comes up with to achieve this is, so delta is the steering angle. So one technique would be having a simple proportional based controller where the amount of steering action applied is directly proportional to the orientation error. So larger the orientation error, more is the steering angle applied, and what that eventually does is it reduces the orientation error of the vehicle. Similarly, a different technique or different control algorithm could be based on the lateral error. So there, the amount of steering angle that you apply is kind of a non-linear function of the lateral error. So the how far away you are from the reference path. And you can see two examples of this technique in this animation. So on the left, you have a pure pursuit path tracking technique. So the red path is the reference that one needs to follow. And you can see a green cross where my mouse is right now. So that's the carrot point in front of the vehicle. And then you can see that the vehicle which starts from with a large error, it kind of converges towards the reference path, and then it kind of keeps trying to follow the carrot point and navigates along the entire trajectory. Similarly, this is a very, very well-known technique called Stanley Controller, which again uses this follow the carrot approach with a controller based on that is based on the lateral error. So a controller, something based on what I mark with my mouse here. And again, it has a carrot point in front of it, which you can see. And you can see that it slowly converges towards the reference trajectory. And then once you reach the reference trajectory, it tries to follow it as closely as possible.